Buckley Farms produces homemade potato chips that it sells in bags labeled 16 ounces. The total weight of each bag follows an approximately normal distribution. That's important. With a mean of 16.5 ounces and a standard deviation of 0.12 ounces. Our first question here, if you randomly select one bag of these chips, what is the probability that the total weight is less than 16 ounces? So we're trying to answer probability that, we'll use the random variable, x is less than 16. All right, that's what we're trying to answer. So let x equal the weight in ounces of a randomly selected bag of chips. All right, we know that x is approximately normal. All right, we can say that it is normal with a mean of 16.15 and a standard deviation of 0.12. Right, so remember, this is our notation to show that something is normally distributed and how we can describe it with mean and standard deviation. All right, so now, since this is normally distributed, right, we're trying to calculate a probability of a normal distribution, so we can use a z-score in table A. So we need to standardize 16. All right, so we get z equals 16 minus 16.15 over our standard deviation is 0.12, and we end up with negative 1.25. If we find this value on table A, we will get, well, so this is the value we're going to look up on table A, and we are going to solve the probability that z is less than negative 1.25. And looking this up on table A, we get 0.1056. Right. And that is the probability that x is less than 16. Right, so then we write our answer. Right, so there is a 0.1056 probability that a randomly selected bag of chips has a weight less than 16 ounces. And we're done with part A. Moving on to part B. If you randomly select 10 bags of these chips, what is the probability that exactly 2 of the bags will have a total weight less than 16 ounces? Right, so identify the variable, let y equal the number of bags less than the weight, with weight less than 16 ounces. So we need to solve the probability that y equals 2. Since we are choosing from a finite number of bags, we're going to see what's the probability of getting 2 of those 10 that have a weight of less than 16 ounces. This is going to use the binomial probability formula. All right, so in this case, we're going to have 10 choose 2 times the probability of the bag being less than 16 ounces, which we just calculated in part A, which is 0.1056. All right, we have 2 times the probability of being equal to or greater than 16 ounces, which is 0.8944 times 8. Right, so 8 plus 2 is 10, the total number of things we're choosing from. I have 2 successes, 8 failures, essentially. And running this through a calculator, we will get 0.2055. right? And so that gives us the following statement. So there is a 0.2055 probability, about a 21% chance, that exactly 2 bags will have a total weight of less than 16 ounces out of 10 randomly selected bags of chips. Sweet. So let's move on to part C. Buckley Farms ships its chips in boxes that contain 6 bags. Okay, the empty boxes have a mean weight. All right, so now we're talking about empty boxes have a mean weight of 10 ounces. And a standard deviation of 0.05 ounces. Calculate the mean and standard deviation of the total weight of a box containing 6 bags of chips. We have also the following. Z is equal to the sum of 6 random bags of chips. All right. T is equal to B plus Z. First of all, we need the mean and standard deviation of Z. Right? We already have a mean and standard deviation of B, right? And so then we'll be able to do the rest of our calculations once we have Z figured out. Right, so we have the mean of Z, 96.9, because the mean of the sum of random variables is the sum of the mean of those random variables, right? So we get 96.9. Right, the standard deviation now so recall up here, T equals B plus Z as far as random variable goes. So if I want the mean of T, I take the mean of B and add the mean of Z. Right, and the mean of B was 10, plus the mean of Z is 96.9. That equals 106.9 ounces. All right, that's the mean of T. And again, standard deviation, we have to do the variances first. So the variance, the variance of T equals the variance of B plus the variance of Z. All right. And we get 0.05 squared plus 0.0864, right, this number up here. Right, we add those guys up, we get 0.0889, which then gives us the standard deviation. That gives us the standard deviation, square root of 0.0889, which equals 0.2982. And now we have figured out the standard deviation and the mean for the weight of a box with chips. All right, and there we go. So a little bit of working around there, but we get there. Lastly, we get that Buckley Farms decides to increase the mean weight of each bag of chips so that only 5% of the bags have weights that are less than 16 ounces. Assuming that the standard deviation remains at 0.12 ounces. What mean should Buckley Farms use? All right, so that's the question we're answering. Now, so we need to find the proper mean, right? So that the probability of x being less than 16, this is the same x we've been using, x representing the weight of a randomly selected bag of chips, needs to equal 0.05, or 5%, right? So we go to table A, and we find 0.05 in the interior of the table, or as close as we can get, right? And that gives us a z of negative 1.645 approximately. Now I used 1.645 because there's actually two numbers close to 0.05. One is 0.0505 and one is 0.04505. So they're both the same amount away, so I split the difference. So instead of using either 1.64 or 1.65, I used 1.645 to be in the middle. And so that's where I got that number. So now we have our z, so we use this number, negative 1.645, and that needs to equal 16 minus whatever the correct mean is, divided by 0.12. Right, this is the value that we're trying to find as the mean weight that they should use. So then we solve for mu of x. Point 1974 equals the mean for a bag of chips, so that we'll only have 5% of the bags having weights that are less than 16 ounces. Right, so then to write this out, we get the following statement. Alright, so they should use a mean weight of about 16.2 ounces to make sure less than 5% of the bags are under 16 ounces. Alright, so here's our next example. In this example, we're talking about the number of broken eggs in a randomly selected carton of 1 dozen store-brand eggs at a local supermarket. Suppose the probability distribution of y, right, and we're using y here, is as follows. Alright, so we have our little probability distribution here, and we want to answer what is the probability that at least 10 eggs in a randomly selected carton are unbroken. So this means that I can have 10, 11, or 12 unbroken eggs, which also means I can have 2, 1, or 0 broken eggs, right? This relates to my probability distribution that I have for y, because y represents broken eggs. So the probability of y being less than or equal to 2 equals the probability of y equaling 0 plus probability of y equaling 1 plus probability of y equaling 2, right? And these we get directly from our table here, right? We have 0, 1, and 2 here. So there is a 0.96 probability, or 96% chance of having at least 10 eggs being unbroken in a randomly selected carton of store brand eggs. Next, we're going to calculate and interpret the mean of y. All right. So the mean of y is equal to the probability of each outcome happening times that outcome. Alright, so over the course of selecting many, many cartons of eggs, there will be an average of 0.38 broken eggs per carton. Next, we'll calculate and interpret the standard deviation of y. And we get to show our work, right? So again, when calculating our standard deviation, we'll first do the variance, right? And we'll imagine that this here has all the rest of my calculations, and we get 0.6756. Right. And we know that our standard deviation is equal to the square root of 0.6756, which is 0.8219. So now the standard deviation is 0.8219, and we get this statement. So on average, the number of broken eggs in a randomly selected carton will vary from the mean, 0.38, by about 0.8219 broken eggs. So now part D, we have a quality control inspector at the store. It keeps looking at randomly selected cartons of eggs until he finds one with at least 2 broken eggs, and find the probability that this happens in one of the first 3 cartons he inspects. Okay, so first, you need to find the probability of y being greater than or equal to 2, right? And this goes back to our original probability distribution. If we're looking at greater than or equal to 2, we're looking at these 3 probabilities. We'll add those up, 0.07 plus 0.03 plus 0.01, we get 0.11. Alright, so we get 0.11. Alright, and in this case we're going to consider that a success. Alright, so this means the probability of selecting a carton with more than 2 broken eggs is about 11%. Alright, so we'll use a p of equal to 0.11, and again this is we're going to let a new variable come to light here. We'll have alright, so that means we're going to find the probability that this happens in the first 3 cartons inspected. So we can have the probability that happens in the first carton, second carton, or third carton. Right. This is a geometric probability. This is geometric. Right. So that means we use the formula P of x equals k is equal to the probability times 1 minus the probability of success times to the power of k minus 1. Right, and so we are using 0.11. So in this case, for p of x equaling 1, we have the sum of these, right? All of these added up is probability of x being less than or equal to 3, right? The first 3 boxes. Alright. So that essentially means that the probability of selecting a carton with at least 2 broken eggs in the first 3 inspected cartons is about 29.5%. Alright. Alright, so here's our next example. We have the Ladies' Home Journal magazine reported that 66% of all dog owners greet their dog before greeting their spouse or children when they return home at the end of the workday. Assume that this claim is true. Right, so we're going to be able to use that data. Suppose 12 dog owners are selected at random, right? And let X equal the number of owners who greet their dog first. So we're already given a random variable. We'll use X. Okay, explain why it is reasonable to use the binomial distribution for probability calculations involving X. To explain this, right, we need to check bins. Right? Is it binary? Is it independent? Is there a fixed number of trials? And is there a fixed probability of success for each sample? Right? So we'll check bins. So first, so we've checked bins. It's all good. All right, so that means it is reasonable to use a binomial distribution for the probability calculations involving X. Part B, only 4 of the owners, right, only 4 in the random sample greeted their dogs first. Does this give convincing evidence against the Ladies' Home Journal claim? Right, so we're ultimately trying to answer this question. Calculate an appropriate probability to support your answer. So this is what we need to do to support our answer. All right, so what we want to do, right, is we're going to calculate the probability of X being less than or equal to 4. What are the chances that 4 or less of the owners greeted their dog first just by chance, right? So to do this, we use our binomial probability formula, but we need to calculate it for 0, 1, 2, 3, and 4. Okay, remember, these two numbers should always add up to this number. All right, 8 plus 4 is 12. All right, 11 plus 1 is 12. 12 plus 0 is 12. All right, so that's how you can know if you've got the kind of the right mix of numbers at the very least. All right, so we do all this, right? And you're most likely going to have to do these in your calculator individually, right? But we end up with 0.0213. All right, so we get approximately 2%, we'll say, chance of 4 or less successes. All right. So, because there's only a 2% chance, right, of 4 or less owners greeting their dogs purely by chance, right, this gives us strong evidence against the Ladies' Home Journal claim, right? So we can write this up in this way. Right, so we get, yes, this provides convincing evidence against the Ladies' Home Journal claim because the probability of 4 or fewer people greeting their dog first just by chance alone is so low, right, at 2%. In this example, we have two students, Ed and Adelaide, and they attend the same high school but are in different math classes. The time E that it takes Ed to do his math homework follows a normal distribution with a mean of 25 minutes and standard deviation of 5 minutes. So we have E, right, and it's approximately normal. And we can represent that as n 25, 5. All right. Adelaide's math homework time A follows also a normal distribution with a mean of 50 minutes and standard deviation of 10 minutes. Assume that E and A are independent, right? That's important. We get to assume these are independent random variables so we can do stuff like variances and such. So we get that. All right, so we also have A, that's approximately normal, with n 50, standard deviation 10. Right? So now, here's our question. Randomly select one math assignment of Ed's and one math assignment of Adelaide's. Let the random variable D be the difference in the amount of time each student spent on their assignments. All right, so we have D equals A minus C. And remember, when subtracting random variables, the order matters. All right, we're going to find the mean and standard deviation of D. And we need to show our work. So, we already have the mean and standard deviation for E and A separately, right? Now, when finding the mean, right, we'll do that first. All right. Next, standard deviation. Now, again, we always add variances, whether we're adding or subtracting random variables, right? So that means that for this calculation, we will first calculate standard deviation of D, which will equal the standard deviation, or the variance of D, which will equal the variance of A plus the variance of E. Right? We're just told to find these things. We don't need to describe them within the context, so we're done. Right? So now part B, find the probability that Ed spent longer on his assignment than Adelaide did on hers. Show your work. So we're going to find the probability that the difference is less than 0. Right? This is what we need to find. This means that Ed takes longer, right? And that is because A minus E would be less than 0. For this to happen, E needs to be bigger than A. All right? So this is what we're looking for. So to do this, we use the fact that we have a normal distribution. When you take the sum or difference of two things that are normal distributions, we still have a normal distribution. So we will standardize 0. So that means we get the following. So there is a 1.25% chance that Ed spent longer on his assignment than Adelaide did on hers. And we are done. All right, our next example here. According to the Census Bureau, 13% of American adults aged 18 and over, so we're going to want that 13%, are Hispanic. An opinion poll plans to contact an SRS of 1,200 adults. All right, so we're going to take a random sampling of 1,200 adults, a simple random sample. All right, what is the mean number of Hispanics in such samples? What is the standard deviation? All right, so if we're given a sample, right, we're doing an SRS of 1,200, right? We want to figure out the mean and standard deviation. Well, one thing we can do here is we can actually use a binomial distribution, right, and use the binomial probability formula to help save some time here. And we'll use the binomial distribution that is that can be used with a normal approximation, right? And we can do this because, right, 1,200 is less than 10% of the entire population. All right, so we pass the 10% condition. All right, this means we can use binomial distribution that can use a normal approximation to calculate probabilities. This is good news. Right, so we call that in these cases the mean, right, equals n times p, and the standard deviation will be the square root of n p times 1 minus p, right? N represents the sample size, in this case 1,200, and p equals essentially a probability of success, which we have as 13% or 0.13. Right, we're going to have a random variable here. We'll let h, so we'll let h equal the number of Hispanics in the sample. Right, so then we get the mean of h equals 1,200 times 0.13, which is 156, and standard deviation of h equals the square root of 1,200 times 0.13 times 1 minus 0.13, or 0.87, and that will equal 11.65. Right, so we have a mean of 156, standard deviation of 11.65. And we're done with part A. Part B. Should we be suspicious if the sample selected for the opinion poll contains 15% Hispanic people? Compute an appropriate probability to support your answer. All right. So first, what's 15% of 1,200? Right. So that's what we'll do first. Right. 15% of 1,200 equals 180. All right. So then to answer this question, right, we want to say what's the probability that our sample has 180 or more Hispanic people, right? So we will find probability of H being greater than or equal to 180, which, remember, greater than or equal to doesn't show up in our table A. So we're gonna use the rule that I can do this is equal to 1 minus the probability of H being less than 180. So we'll standardize the 180. We will find 2.06 on table A to find the probability to the left of 2.06. All right, and that gives us the probability of Z being less than or equal to 2.06 equals 0.9803. Right, this now goes in place of that. So we'll now do our calculation here. The probability of H being greater than or equal to 180 equals 1 minus probability of H being less than 180, or 0.9803, which equals 0.0197, or just about 2%. Right? This is very small. Okay? So we can say the following. Because this probability is so small, it is unlikely that 180 or more Hispanics will be in the sample just by chance. So, we have reason to be suspicious about the sampling process.